Our first talk of the afternoon is by Kiran Kedlaya, and his title is The Relative Cost Number One Problem with the Function Field.
All right, let me start by, I guess I'll have another opportunity to thank the organizers during business meeting, but I'll go ahead and thank the organizer now for pulling an ants together. This is probably one of the most difficult ants to organize in the COVID situation. I've only previous ants. So thank you for that. And the program for committee for the opportunity to speak. A couple of quick things before we get started. These slides are posted on my website. The link is also in Zoom. It's going. So the slides are posted here. That link is also in Zulip. There's a GitHub repository associated to this project. That link is also in the Zulip. And I am watching the chat in the Zulip in case anybody from the online audience posts a question there. I can't promise I'll catch it right away, but give it a shot. All right, and there are disclaimers and reminders below. So the setup for this project is the following. So I'm going to be talking throughout about f prime over f. This is some finite extension of fields, each of which is the function field of a curve over some finite field. So it's some field of positive characteristic of transcendence degree 1 with a prime field. And in particular, it's finite genus. So I'm going to write G sub f and G sub f prime for the genera of these curves. Later on, I'll call these G and G prime. But I'm going to use the subscript right now just for emphasis. Q sub f and Q sub f prime will be the cardinalities of the base fields. So you take the integral closure of the prime field, and its order is Q. If I ever say P, that will be the characteristic, but I don't remember whether I use P anywhere. So each of these, of course, has a finite class number. You sort of ignore we'll get degree 0 divisors modulo principal, degree 0 divisors. That's some finite group. I'll write H sub f and H sub f prime for the respective class numbers. And in this talk, I'm interested in the relative class number, which is the ratio, which is always an integer, for reasons that I'll explain in a moment. And so the relative class number, one problem is when can this relative class number be equal to 1? And as far as I know, this question was first asked by Weitzel and Madan in the 1970s. Now, in order to make this a well-posed finite problem, I have to do one kind of tricky thing and a couple of. I have to kind of cut out a few sources of not finiteness in this problem. One is that if the genus of f is too small, then you might be able to have a given pair of fields with lots of different inclusion maps between them, right? Like if you have a genus 0 function field on the bottom or a genus 1 function field on the bottom, any two maps between the same fields will give you the same relative class number because it doesn't depend on the map, just on the top and the bottom. So I'm only going to look for the isomorphism classes of the field on the top and the bottom and not worry about the map. But if the genus of the base field is at least 2, you can also hope to pin down the maps. There's also the trivial case where f prime and f are isomorphic, not necessarily through the identity map, but any inclusion of genus 0 function fields is of course going to have relative class number 1, so I ignore that. And even so and I also have to rule out the case where it's an extension of genus 0 guys because you might be allowed to enlarge the field. So okay, those are the trivial exceptions, and then the problem is excluding these trivial exceptions give me a finite list of examples and prove that it's complete. First, maybe prove that you get a finite list and then actually identify that finite list. So let me point out something about the number field case. I should warn you, this slide is not really reflected in the paper yet. I will update it in the final version. In the number field setting, class number 1 is somehow much more common because class groups are somehow missing an Archimedean contribution. The thing that behaves more predictably is the class number times the unit regulator, which is the volume of the sometimes called the Arkelov class group. And so in particular, you can only talk about the relative class number of one problem in a situation where the extension preserves the unit rank. And if you've taught algebraic number theory, you've maybe made your students check that this only happens when you take a totally positive, a totally imaginary quadratic extension of a totally real field, take a CM field. So I don't know if there's a general theorem that says that you have a finite bound in the number field case. It's definitely the case that for normal CM fields, normal over Q, the finiteness follows from Odlyzko using his bounds on discriminants, and the full classification was done quite recently by Hoffman and Sircano. I think this is a 2020 preprint on arXiv. I couldn't find the public version. So this is, as far as I know, it's an open problem to do the relative class number one problem in the non-normal case, although there's some partial work. By contrast, when you're talking about function fields, there's not this concern about the unit rank. So you can really ask this question about arbitrary extensions as long as you take out the trivial exceptions. Okay. So I'm going to distinguish two subcases. I'm going to say a function field extension is constant if it is the compositum of the base field with some finite field. So that doesn't change the genus, of course. And then the opposite extreme is that I have a geometric extension if the base field doesn't change. So this might be what you were thinking of when I wrote this thing down in the first place. And indeed, most of the talk will be about this geometric case, because that case is more interesting. But we do actually cover both cases. There's also, of course, a mixed case, but you can handle the mixed case by saying, well, if you have a general extension of function fields, and in between, you can put the composite of the base field with the base function field with the constants of the larger field. And then since the relative class number is an integer, relative class number one implies relative class number one for the two sub-extensions. And so once you solve the two subcases, it's quite easy to put everything together. So, and I'll also just maybe say that the constant case is relatively easy. It's only about 2 pages of the paper. So for the rest of the talk, I'm going to focus on this geometric case. So from now on, Q is the common constants of both function fields, and I'll write G and G prime for the genus of the downstairs and the genus of the upstairs. So, so the first thing you have to do with one of these problems is reduce to a finite computation. So let me describe a reduction of this problem to a finite computation. You have to be careful in the back because it blocks the camera. So I'm going to write C and C prime for the curves with function fields F and F prime. And here's why the relative class number is an integer. The Jacobian of the upstairs curve is isogenous to the Jacobian of the downstairs curve times some abelian variety, which is often called the prim variety for the covering. So, and the point is that the relative class number is just the order of the group of FQ rational points. So that's certainly an integer. And not only is it an integer, this interpretation gives this integer a lot of useful structure. It's going to relate it to Bay polynomials and so on. So this is a sort of key point, that this relative class number is the order of some group of rational points of some abelian variety. And so we're interested in the situation where this abelian variety has order 1, and F prime is not equal to F. Well, that can't happen very often. It can never happen when Q is at least 5, because the Bay bounds tell you that when you have a non-trivial, non-zero abelian variety over a finite field of order at least 5, then you get a non-trivial, lower bound greater than 1 for the number of points. For Q equals 3 and 4, you also have very limited options. This A has to be isogenous to a power of, there's one elliptic curve over FQ with a single FQ rational point, and A has to be isogenoous to a power of that. Now, what makes this interesting is that when Q equals 2, things break loose. There is a classification of the simple abelian varieties of order one, but there are actually infinitely many of them. This sort of goes back to work of Madan and Paul, which is inspired by work of Raphael Robinson on algebraic integers in short intervals, all of whose conjugates lie in short intervals. So you have this classification, it's somehow based on the sort of index by roots of unity, but there's kind of a lot of cases to worry about. And so this sort of suggests why Q equals 2 is going to be much harder than Q equals 3 and 4. And so you'll see that there are some steps where Q equals 2 is significantly more work. Okay, so how do I use this prim variety? Well, so if I just look at traces, T A Q to the n is going to be the trace of Q to the n power Frobenius on A, then the number of points on C is equal to the number of points on C prime plus the trace of A. Right, it's plus because there's a minus sign in the leftist trace formula. And of course, the number of points on C prime is non-negative. So this trace is a lower bound on this point count. And that's handy because when Q equals 3 and 4, this trace is going to be, the Q trace is going to be Q times the dimension of A, because I have a power of an abelian variety of order 1, its trace is Q. So because Q plus 1 minus Q is what gives you 1. And so you have Q times the dimension of A. The dimension of A is G prime minus G, which by Riemann-Hurwitz is at least G minus 1. So that's a pretty strong lower bound on point counts. For Q equals 2, something goes wrong. You find very quickly that there's an example which has trace 0, so you're not going to get much of a lower bound, but like this. But you can get a lower bound that involves the traces of over F2 and some higher powers. So you do a little bit of linear programming and you use this estimate, you sort of use this classification, and you also cheat and you look at LMFDB for small dimensions because it's easier. And you get some sort of weird lower bound on some linear combination of traces. Now, why is this a reasonable thing to work with? Well, I sort of telegraphed this by using the phrase linear programming. Right? The reason why I want to have a lower bound on point counts is because I want to put this in opposition to an upper bound on point counts. Well, where do upper bounds on point counts on curves come from? They come from the linear programming method, which you can find, for example, in Sarah's lecture notes on rational points on curves over finite fields from Harvard in '85 were recently published by the SMF. So you can read Sarah's description of the Ihara, Drinfeld, Vladutz, Österle method for getting these effective upper bounds on point counts. And well, for Q equals 3 and Q equals 4, I just look up point counts from the tables, and I see that the asymptotics are much slower, these upper bounds grow more slowly than my lower bounds. So eventually I have the tension. For Q equals 2, I have to take advantage of the fact that these linear programming methods don't really directly give you bounds on the number of points over FQ. What they give you is some sort of bound on some linear combination of the numbers of places over various degrees. So you can, if you kind of work the linear programming method, you can get some upper bound that involves places of degree 1 through 4 of this sort of shape. And I've sort of carefully constructed these upper and lower bounds so that they are in fact in tension. Right, I had a 1.56 in the bottom right corner over here, and I have a 0.8042 over here. That's quite a bit of tension. So that gives me an upper bound on G and therefore on G prime because of Riemann-Hurwitz. Yay, I've reduced the problem to a finite computation. However, if you look at the numbers, for example, the bound on G in this case is something like 40. So I haven't reduced this problem to a doable finite computation yet. So there's more work involved to actually make this finite computation, get it down to a tractable size, and then to do it. And this is mostly finished in the paper that I'm presenting. There are a couple of loose ends, which is why this paper has a part 1 in the title. I'll mention the loose ends as I go. So let's sketch how this finite computation gets done, modulo the loose ends. So again, I only want the isomorphism classes of CMC prime and not the map. Although once the G is at least 2, I'll get the map as well. Okay, what do I do? For each possible pair G and G prime, I have a finite list of, okay, so for each Q, I should have quantified, Q equals 2, 3, or 4 and what follows. So for each possible pair, for each possible Q, you enumerate candidate Weil polynomials for C and C prime. So I have code for this that I wrote sort of starting in 2008, which is integrated in Sage, so you can fire up Sage and ask for a list of Weil polynomials. So for G, right now I'm assuming G is less than or equal to 1, so you can just do this in the range. You only have to go up to G prime equals 7. So for each pair of Weil polynomials that you get, you check LMFDB to identify all the curves of those Weil polynomials. This mostly works because LMFDB has data about curves of genera up to 5. So genus up to 3 was contributed by Everett Howe, genus 4 by Xavier Charles, and genus 5 by Dusan Dragutinovich, a student of Karl Faber. Unfortunately, I need 2 cases where G prime equals 6. One of them conveniently was ruled out by a preprint of Grantham, Howe, and Faber. This is Xander Faber, not Karl Faber. That paper hit archive less than a week ago. So you can find that argument there. The other case, you can't rule it out because it actually occurs. Conveniently, it shows up elsewhere in my calculation as a cyclic 5-fold Natal cover of some genus 2 curve. There is a loose end to prove that this is the only way that this Weil polynomial can occur. But modulo that one loose end, I've kind of completely covered the case where the bottom genus is at most 1. Now, what happens when the bottom genus is bigger than 1? So now what I do is, well, I have some information also about the degree of the extension coming from Riemann-Hurwitz. And if you've ever played around with rational points on terms of these sort of, trying to improve the tables on many-points.org to get upper bounds on numbers of points on curves over finite fields, you spend a lot of time making arguments that involve the degree of the extension. You sort of figure out what ways the primes downstairs can split upstairs, and you get various bounds. So people like Everett Howe and Kristenwater and so on have spent a lot of time thinking about this. You kind of use those ideas, and this gives you a much better bound on G and G prime. So this gets you down to about G equals 9, I think is the worst case. So you have a handful of triples left. And now for each of these, you actually enumerate Weil polynomials. The hard case is you have to find all the Weil polynomials for basically all curves of genus 9, given some constraints on F2 and F4 points. So that takes about 30 minutes using my code. All the other cases are cheaper. So you kind of do some exhaustive Weil polynomials. And then you have to figure out where to get curves C with a given Weil polynomial. I don't have to worry about C prime just yet. I have to worry about where C is going to come from. So fortunately, the worst case that actually survives the previous step is G equals 7. But there are some cases with G equals 6 and G equals 7 that are not covered by LMFDB. I'll come back to this. So if you know all the possibilities for C, now you kind of forget your knowledge about C prime. you just look for all extensions, well, let's say all cyclic extensions of the right degree and genus, and then you check the relative class number for those. And well, if D equals 2, then you're happy because all extensions are cyclic. But if D is bigger than 2, you have another step that you have to do, which is you somehow have to argue that you didn't miss anything that wasn't cyclic. I mean, a priori, you don't know that there isn't going to be anything that's not cyclic. It turns out that there isn't. For Q greater than 2, it turns out you only have to worry about degree 3 extensions, and this is not so difficult. I'll say something about the Q equals 2 version when I talk about loose ends, which is now. So yeah, so if you look at the paper I'm presenting, I've sort of done it end to end for Q equals 3 and 4, but for Q equals 2, there are a couple of loose ends, namely the following. As I said, for G equals 1, G prime equals 6, I need to find all the genus 6 curves with a particular Weil polynomial, and Everett has a nice technique that uses the particular shape of this thing to force there to be an order 5 automorphism of C prime, more or less does it. I have to worry about finding all the base curves with where that have extensions of a degree at most 7, and I have to worry about these non-cyclic extensions. Well, non-cyclic extensions of degree up to 7 can be quite complicated. What you end up doing is you exhaust over the possibilities for the Galois closure, for the Galois group, the Galois closure. There aren't so many of those. You find other curves in that tower of fields, and you examine the point counts of those. So this is an idea that's been used by Rigato in the point counting, in the problem of bounding numbers of points on curves. But getting it up to D equals 7 requires some elaborate representation theory. You have to worry about A5 and A6. And okay, there's one other loose end, which for the quadratic extensions, where I don't have this non-cyclic problem, I have to find curves of genus 6 and 7 on the bottom with a given Weil polynomial. So this, in principle, you can enumerate over the moduli space of curves of these genera. In practice, it's a little bit elaborate, so that's not done in this paper. But I have 2 preprints posted that take care of one of the. So paper number 2 takes care of the first 2 issues in this list. Paper number 3 takes care of the third one. So if you want to read about those loose ends, there is something that you can read. But I'm going to state theorems, not assuming those results. So these are conclusions just based on this paper. I'll do one more thing. So yeah, so if you have an extension f prime over f which is constant, so I'm kind of dropping that geometric hypothesis. If I allow the constant case, then there's a very small number of possible triples, base field size, degree, and genus of the base field. And I have a complete table of these in the paper. Likewise, if you have an extension which is geometric and the base field has dimension genus of most 1, then as you see, I have Q equals 2, G prime equals 6 as an option. There aren't very many options for Q equals 3 and Q equals 4, and everything is pinned down perfectly except when G prime equals 6. If you have the base field genus bigger than 1, but Q is bigger than 2, I completely deal with that case. If you have G bigger than 1, Q equals 2, and the degree is bigger than 2, I completely deal with that case, except that I don't treat the non-cyclic options yet. I put the stars here because there are some options that come out of Weil polynomials that don't show up for any cyclic extension, probably just because there aren't enough options that survive. And there's a big cut down between how many Weil polynomials you get and how many fields you actually get. Because if you kind of are forced to make an extension of some base field, class field theory doesn't sort of privilege any of the options that are eligible for the top curve, and you might not get the one that happens to give you relative class number 1. And then finally, for D equals 2, You have a complete classification except when the base field has genus 6 and 7, because that computation is not included in this paper. But I do have examples for both of these. There are at least 2 examples with G equals 6 and at least 1 with G equals 7. You can ask me afterwards how I found the story. And I want to finish because, well, by saying, well, what about relative class number m when m is bigger than 1? It's a natural thing to do. Haven't looked at it. There are 2 things you would have to do differently. So these are kind of invitations for future work. One is that, well, you're not going to classify abelian varieties over F2 with a fixed order. That's just a mess. But you should be able to get a useful lower bound on some linear combination of traces under the assumption that the order of the abelian variety is fixed. So that would be an interesting thing to work out. It probably won't be as sharp as for m equals 1, but if it's good enough, you might be able to solve some small m cases using this approach. The other thing, of course, you have to do is you have to worry about non-cyclic extensions. Because I got lucky for m equals 1 and I didn't end up finding any non-cyclic extensions. But for other values of m, you probably will start to see some. So for that, you need some good way to enumerate degree d extensions of a fixed function field. And my guess is that for d up to about 5, the right way to do this is to use Pargov-style parametrizations. For d equals 3, this is the Dalvinport-Halbrun/Delaunay-Fadeev parameterization. And I think Karim Belabas implemented this as well back for cubic number fields. So the number field setting over Q, this was implemented. He has a package called cubic that does this, but I want to do this over arbitrary function fields. So there's an implementation project. That would be interesting. All right, that's all I got. Thanks.
Question to the speaker.
So for the first open question, do you really think this is feasible for any fixed m, or are you thinking more starting with small m's?
I mean, I think it should be the case that given m, you should be able to get some bound that's a function of n. I have no idea how reasonable that bound would be, but I imagine, right? Because once, I mean, for any given m, for a of small dimension, there's not very much of a constraint, but once a is a big enough dimension, it becomes a pretty serious constraint, right? Because m somehow gets quite small compared to the dimension. So in that case, I do expect that there's some linear program argument that you could do that would give you a reasonable bound as a function of m. I have no idea what exactly that would look like, but it seems plausible. Yeah.
Is it known that it's finite, Jim?
That what's finite?
There's finitely many.
No, there aren't finitely many. Even for m equals 1, there aren't finitely many.
Right.
So that's why it's hopeless to classify. Well, yeah, already for m equals 2, it was a non-trivial task to prove that there are infinitely many simple abelian varieties of order 2. And it seems hopeless to classify. So your best bet is to get a good linear programming argument and then use that to get a bound on genus, get yourself down to a finite computation that way. And then, okay, you have to worry about the ones of small order of low dimension, but that you can hopefully just enumerate.
Any other questions? If not, let's thank Kiran again.